You hear about interstellar visitors all the time now. Dark streaks against stars, mysterious trajectories, headlines screaming alien tech. But nobody talks about what actually happens when frozen rocks from another star system slam into our sun's radiation field at 70 kilometers per second. The physics gets ugly fast. It came from somewhere else. It is passing through, and nothing in our solar system will ever see it again. Nobody could explain it. Second was 2I Borisov in 2019. Looked almost normal until you checked the chemistry. Carbon monoxide levels that made no sense for our neighborhood. Higher than Borisov's 3.4. 6.137 makes the trajectory look nearly straight. A bullet fired from deep space, and we are standing in the firing range for exactly 5 months. October 29th, 2025 at 11:47, universal time plus or minus 1 minute. Distance at Perihelion, 1.36 astronomical units. 203 million kilometers, 126 million miles. That puts it between Earth and Mars, inside the warm zone where ice starts screaming into gas. That speed combined with solar radiation creates a pressure environment that rips molecules apart at the atomic level. This script is researched and factual, using sources from the James Webb Space Telescope Near-Infrared Spectrograph Observations, published August 6, 2025, the Nordic Optical Telescope Pre-Perihelion Study, published October 21, 2025, in Archive 2510.18769, and the European Space Agency Tailcatcher Ion Tail Crossing. Prediction paper Archive 2510.13222, published October 15, 2025. These are not press releases. These are peer-reviewed observatory data and spacecraft trajectory calculations. Now back to the physics. At Earth's orbit, the density drops to around 5 particles per cubic centimeter. That sounds empty. It is not. At those velocities, even thin plasma carries enough momentum to sculpt comet tails millions of kilometers long. When 3I Atlas crosses into the inner solar system, 2 things happen simultaneously. The sun's heat vaporizes surface ice. Ultraviolet radiation ionizes the gas. Neutral molecules become charged particles. Water becomes H2O+. Carbon dioxide becomes CO2+. Carbon monoxide becomes CO+. These ions do not drift. They get grabbed by the solar wind's magnetic field lines and accelerated outward at hundreds of kilometers per second. It always points directly away from the sun because magnetic field lines in the solar wind point radially outward. The ions are charged, so they follow those field lines with near perfect alignment. Radiation pressure affects them far less than the magnetic coupling. You can see the difference between an ion tail and a dust tail from telescopes on Earth. Dust reflects sunlight and curves along the orbital path. Ion tails glow from fluorescence and point like laser beams away from the sun. 3I Atlas reaches peak activity near perihelion because that is where solar heating peaks. More heat means more sublimation. More sublimation means more gas. More gas means more ions. The ion production rate scales with heliocentric distance to a power law. For 3I Atlas, observations from the Nordic Optical Telescope between July and September 2025 measured a heliocentric index of 3.8 plus or minus 0.3 across the range of 4.6 astronomical units down to 1.8 astronomical units. That index of 3.8 corresponds to dust production rates varying as heliocentric distance to the negative 1.8 plus or minus 0.3 power. A heliocentric distance to the negative 2 power variation is what you expect for a strongly volatile material, carbon dioxide. Independent spectroscopic observations confirmed carbon dioxide is the primary driver of activity on 3I Atlas. James Webb Space Telescope aimed its near-infrared spectrograph at 3I Atlas on August 6, 2025. When the comet sat 3.32 astronomical units from the sun, Webb found something nobody expected. The coma composition ratio of carbon dioxide to water was 8:1. 8 times more carbon dioxide than water. That is the highest CO2 to H2O ratio ever recorded in a comet. On August 6th, the nucleus was ejecting 129 kilograms of carbon dioxide per second, only 6.6 kilograms of water per second. Carbon monoxide added 14 kilograms per second. Carbonyl sulfide added 0.43 kilograms per second. Sphere-X Space Observatory confirmed those numbers independently from mid-August observations. Sphere-X mapped a massive carbon dioxide gas cloud extending at least 348,000 kilometers from the nucleus. That is roughly the distance from Earth to the Moon. The cloud is visible only in near-infrared because carbon dioxide fluorescence peaks at those wavelengths when excited by solar UV. The CO2 frost line sits around 5 astronomical units for a typical solar luminosity star. Water ice frost line sits closer at around 3 astronomical units. If 3 I Atlas formed in its parent star system beyond the carbon dioxide frost line, you get a CO2-rich nucleus. If it spent billions of years in interstellar space at temperatures below 10 Kelvin, the water ice could have been preferentially stripped by cosmic ray sputtering or converted to more stable phases, leaving a carbon dioxide-enriched mantle. A comet gushing carbon dioxide and holding back water. Solar flux scales as 1 over distance squared. Closer to the sun means exponentially more energy hitting every square meter of nucleus surface. A few degrees of surface temperature increase can double or triple the sublimation rate. At 1.36 astronomical units, surface temperatures likely exceeded 200 Kelvin on the sunward side. That is hot enough to sublimate carbon dioxide at rates measured in tons per second, not kilograms. No clear tail structure, just a lopsided coma with jets pointing toward the sun. That configuration is rare but not unprecedented. It happens when large dust particles around 0.1 millimeters effective radius get ejected slowly at roughly 5 meters per second. Those particles respond sluggishly to radiation pressure because they are heavy. They spread out in the direction of ejection before radiation pressure can turn them around into a classic antisolar tail. Gemini South Telescope in Chile captured 3 I Atlas on August 27th. The tail had emerged, a clear antisolar structure extending 50 arc seconds, or approximately 100,000 kilometers in angular length as measured from Earth. The tail grew from 30 arc seconds and 56,000 kilometers in late August to 50 arc seconds by September 15th. As activity ramped up approaching perihelion, smaller, faster-moving particles began to dominate the scattering cross-section. Micron-sized grains ejected at tens of meters per second respond quickly to radiation pressure. They get pushed antisolar within hours. The tail became visible because the population shifted from heavy, slow dust to lighter, faster dust mixed with glowing ions. This mass loading creates a bow shock upstream of the comet nucleus. Behind the shock, the magnetic field lines drape around the comet like an umbrella folding in on itself. Bundles of field lines loaded with ions form the visible ion tail structure. The interaction between solar wind and cometary ions involves pickup ion physics. A neutral molecule sublimates from the nucleus. UV photons ionize it. The newborn ion sits nearly stationary in the solar wind frame. Then, the solar wind magnetic field sweeps past at hundreds of kilometers per second. The ion gets picked up and begins gyrating around the field line at the local gyro radius. For heavy ions like water or carbon dioxide, the gyro radius can be hundreds of kilometers. The ion spirals outward while also being convected antisolar by the bulk flow. The pickup process transfers momentum and energy from the solar wind to the cometary ions. This loading slows the solar wind and deflects it around the nucleus. If the ion production rate is high enough, the magnetic field lines get squeezed together until they reconnect downstream in the tail. Reconnection releases magnetic energy and can sever the tail completely in what is called a disconnection event. The current sheet is the boundary where the interplanetary magnetic field flips polarity from pointing north to pointing south. When the polarity reverses, the old tail with one polarity gets cut off and drifts away. A new tail with the new polarity starts forming from scratch. Comet Encke experienced a complete tail disconnection on April 20th, 2007, when it passed through a coronal mass ejection. Stereo spacecraft watched the event in real time. 3. I Atlas could experience disconnection events near perihelion if it crosses the heliospheric current sheet while ion production is peaking. The current sheet undulates above and below the solar equatorial plane. 3. I Atlas trajectory is tilted 175 degrees retrograde with respect to the ecliptic, which means an inclination of 5 degrees. That brings it close to the current sheet multiple times during October and November. Near perihelion, ion tail width and intensity should reach maximum because solar wind interaction intensity scales with gas production rate. Higher production means more pickup ions. More pickup ions mean more mass loading. More mass loading means more magnetic draping in a wider region where cometary ions get accelerated antisolar. Water production will also increase but remain a minor component compared to carbon dioxide. Carbon monoxide and carbonyl sulfide will add to the total. The combined outgassing creates a dense coma with a radius potentially reaching hundreds of thousands of kilometers when you include the tenuous outer regions. Solar wind flows in from the sunward side at 400 to 600 kilometers per second. It hits the neutral coma. Charge exchange occurs. Solar wind protons steal electrons from neutral molecules, creating ions. Photoionization from solar UV creates more ions. The newborn ions immediately start getting picked up by the magnetic field. For an active comet near perihelion, the bow shock standoff distance can be tens of thousands of kilometers. Behind the shock, the plasma becomes turbulent. Magnetic field fluctuations increase. Waves propagate through the plasma. The region behind the shock and in front of the nucleus is called the cometosheath. It is analogous to the magnetosheath around Earth, but formed by mass loading instead of a planetary magnetic field. The draping pattern depends on the upstream field orientation and the symmetry of the gas production. For a comet with strong jets pointing in specific directions, the draping becomes asymmetric. 3, I-Atlas, showed asymmetric jets in early observations. The coma on September 15th was elongated along the anti-solar direction, indicating stronger outgassing on the sunward hemisphere. The tail contains a current sheet in the center where field lines of opposite polarity meet. Above the current sheet, field lines point one direction. Below the current sheet, they point the opposite direction. Ions get accelerated along these field lines by the electric field associated with the solar wind convection. In plasma physics, moving a magnetic field through space creates an electric field perpendicular to both the field and the motion. Charged particles feel that electric field and get accelerated in the direction of the field. For ions in the cometary tail, the electric field points anti-solar, so ions get accelerated away from the sun at speeds approaching the solar wind speed. The result is a stream of ions flowing anti-solar at hundreds of kilometers per second. Tracing out the ion tail visible in images, the tail can extend millions of kilometers. Historical measurements of bright comets have found ion tails reaching 3.8 astronomical units in length. That is 570 million kilometers, from Sun to beyond Mars orbit. But even a modest ion tail extending 1 million kilometers is enormous on human scales. If you could see the tail from the side, instead of looking down the barrel from Earth, it would span several moon diameters in the sky. When Earth looks directly down the tail axis, we see the tail foreshortened. It appears short, even though it stretches far in three-dimensional space. When Earth sits off to the side, we see the tail in profile. It appears longer. 3. I-Atlas. Viewing geometry improves after perihelion as Earth's position relative to the comet changes. Observers in December 2025 should see better tail development in profile than observers in July when the comet was discovered. But here's where the physics gets interesting for spacecraft. Europa Clipper launched October 14, 2024 on a mission to Jupiter's moon, Europa. It is currently en route, performing gravity assists to build up speed for arrival at Jupiter in 2030. On its way, it happens to cross orbital space near where 3I Atlas ion tail will be between October 30th and November 6th, 2025. It is heading outward toward the asteroid belt. Between October 25th and November 1st, 2025, Hera's trajectory places it near the predicted path of 3I Atlas ion tail. Developed by Samuel Grant at the Finnish Meteorological Institute and Geraint Jones at the European Space Agency, Tailcatcher tracks solar wind packets and calculates where cometary ions swept up by those packets will end up in space. The model uses measured solar wind velocities at various spacecraft locations and interpolates the flow paths backward to the Sun. Then it compares those paths to the comet's position in time. When a spacecraft trajectory crosses a path that came near the comet, Tailcatcher flags it as a potential ion tail crossing. In 2020, ESA Solar Orbiter detected ions from Comet C 2019 Y4 after Tailcatcher predicted the encounter. The model works because ion transport in the solar wind is deterministic if you know the wind speed and direction. For 3I Atlas, Tailcatcher calculates the impact parameter for Europa Clipper and Hera. Impact parameter is the minimum missed distance between a spacecraft trajectory and the central axis of the ion tail. For Europa Clipper, assuming a radial solar wind speed of 450 kilometers per second, the impact parameter drops to around 8 million kilometers between October 30th and November 6th. That sounds like a miss, but ion tails are broad. The tenuous outer edges of the tail can extend millions of kilometers from the central axis. Both spacecraft will be far from the dense core of the tail, but they could still intercept pickup ions in the diffuse outer regions if the solar wind conditions are favorable. It can have tangential components that deflect the flow by several degrees. If the deflection is large, the ion packets miss the spacecraft entirely. The wind also has to be strong enough to carry the heavy ions all the way out to the spacecraft distances. Weak, slow solar wind does not convect ions as far. Strong, fast wind carries them farther. The ions have to travel 60 million miles through the solar wind to reach Europa Clipper. At 400 kilometers per second, that transit takes roughly 3 to 4 days. At 600 kilometers per second, it takes 2 to 3 days. The timing has to line up so that ions released from 3I Atlas near Perihelion arrive at Europa Clipper's location when Europa Clipper is there. Europa Clipper carries the Plasma Instrument for Magnetic Sounding, PIMS, which measures charged particles in Jupiter's magnetosphere. It also carries the Europa Clipper magnetometer, ECM, which measures magnetic field. Those instruments are designed for Jupiter environment, but they can detect cometary ions if the signal is strong enough. Cometary ions include water group species, carbon dioxide, carbon monoxide, and other heavy molecules. The mass difference allows identification. A mass spectrometer, or energy analyzer, can separate heavy ions from light ions. PIAMS has energy and mass resolution that should distinguish water ions from protons if the flux is sufficient. The magnetic field strength increases because the field lines pile up as the flow decelerates. This mass loading signature is detectable with a magnetometer. ECM should see a change in field strength and direction if Europa Clipper crosses regions where cometary ions are present. Grant and Jones estimate that if Europa Clipper crosses the tail, it could detect magnetic draping structures, pickup ions, and possibly even small-scale turbulence associated with the ion pickup process. The encounter duration would be days to a week as the solar wind convects the cometary plasma past the spacecraft location. Hera carries optical cameras and a radar designed for asteroid surface mapping. It cannot measure the ion tail directly. Hera will pass through the predicted region without collecting data on the plasma environment. This leaves Europa Clipper as the only spacecraft with a chance to directly sample 3 IATLAS ion tail. Activating instruments requires planning and coordination between mission operations and science teams. Grant and Jones are not on the Europa Clipper team. They published their prediction as a preprint and a research note to alert the community, but the decision to activate Europa Clipper instruments lies with NASA and the mission team. As of October 2025, it is unclear if Europa Clipper will be in the right instrument mode to capture the ion tail crossing. The US government experienced a shutdown in late 2025. Shutdowns can delay spacecraft operations planning. If the instrument activation was not scheduled before the shutdown, the window could be missed. At 8 million kilometers offset, the ion density could be too low to produce a detectable signal above the solar wind background noise. It depends on how broad the tail actually is and how much carbon dioxide 3I Atlas is releasing at perihelion. If 3I Atlas hits maximum activity near perihelion and produces a very broad ion tail, Europa Clipper could get lucky. If activity is moderate and the tail is narrow, Europa Clipper might detect nothing. Execution is hard, data is precious, but the attempt is worth making because this is the closest we can get to a direct sample of material from another star system without sending a dedicated interstellar probe. They seal in material from their formation billions of years ago. When a comet approaches a star, that material gets ejected into space. For 3I Atlas, the material has been frozen at interstellar temperatures below 10 Kelvin, possibly for billions of years. It might not have approached any star more closely than our Sun, since it was ejected from its parent protoplanetary disk. The August observations present an opportunity to study the rise of activity on an object held in deep freeze for longer than Earth has existed. The carbon dioxide dominance tells a story about the formation environment. CO2, ice forms farther from a star than water ice. 3I Atlas nucleus must have formed beyond its parent star's carbon dioxide frost line. That places its formation region at least 5 astronomical units from the star, possibly farther, depending on the star's luminosity and the disk's temperature structure. The 12 carbon to 13 carbon ratio appears close to the terrestrial value, though the measurement is difficult because dust and other gases partially obscure the spectral features. A terrestrial-like carbon isotope ratio suggests the parent star had similar nucleosynthesis history to the Sun. That implies the star was probably not metal poor and formed in a galactic environment with sufficient heavy element enrichment. A September 2025 study traced 3I Atlas backward through this galaxy. Over the past 10 million years, the comet may have passed within 1 parsec, 3.3 light years, of 25 known stars. The exact parent star is unknown, but the comet's dynamical membership in the galactic disk suggests the parent was a thick disk star with metallicity at least 40% of the Sun's. What happens to the nucleus when it absorbs maximum solar flux? The spinning nucleus can break apart if the tensile strength is too low to hold the pieces together under centrifugal stress. Historical comets have fragmented spectacularly near the Sun. Comet Shoemaker-Levy 9 broke into 21 pieces before hitting Jupiter. Comet Linear broke apart in 2000. Comet Ison disintegrated at perihelion in 2013. The James Clerk Maxwell Telescope measured hydrogen cyanide production on September 7th when the comet was 2.33 astronomical units from the Sun. Production rate was 1.5 plus or minus 0.5 times 10 to the 25 molecules per second. By September 14th, the rate had climbed to 4.5 plus or minus 1.9 times 10 to the 25 molecules per second. The increasing production rate indicates the nucleus was sublimating more actively as solar flux increased. The nucleus appeared to be handling the thermal load without fragmenting. If the nucleus has internal structural weaknesses, they will fail at perihelion. The comet could break apart, or it could survive intact. If it fragments, multiple nuclei could produce multiple ion tails. Fragmentation events create complex plasma interactions because each fragment generates its own coma, an ion cloud. The fragments can interact with each other's plasma, creating turbulent regions between them. 3. I-Atlas passed behind the Sun on October 27th. Solar conjunction. Earth cannot observe the comet when it sits too close to the Sun in the sky. Ground telescopes cannot point that close to the Sun without damaging the instruments. Space telescopes in Earth orbit have similar restrictions. During conjunction, 3I Atlas is invisible from Earth. On October 3rd, when 3I Atlas passed 0.19 astronomical units from Mars, both spacecraft attempted to photograph the comet. Distance from Mars to the comet was roughly 28 million kilometers. The comet appeared extremely faint, up to 100,000 times fainter than typical imaging targets. Images show the comet as a fuzzy dot, barely resolved, but the images are historic. First-time spacecraft orbiting another planet photographed an interstellar object. The Mars observations constrain the comet's brightness and activity level during early October. If analysis shows the nucleus brightening faster than expected, that suggests activity was ramping up ahead of perihelion on schedule. If brightness stayed flat, that suggests the comet was not as active as predicted. Amateur astronomers with 8-inch or larger telescopes in dark skies might spot it. Professional observatories will track it closely to see how perihelion affected the nucleus. Hubble space. Telescope plans ultraviolet spectroscopy in November to measure the sulfur to oxygen ratio in the gas emissions. That ratio constrains formation conditions in the parent disk. High sulfur relative to oxygen suggests formation in a sulfur-rich environment. Low sulfur suggests sulfur was depleted or locked into refractory grains. If the surface was carbon dioxide rich and the interior is water rich, the post-perihelion spectrum should show higher water to carbon dioxide ratio as fresh material gets exposed. Hydroxyl is the breakdown product of water in the coma. UV photons split water molecules into hydrogen and hydroxyl. Hydroxyl fluoresces at UV wavelengths. Measuring hydroxyl production rate gives water production rate. Swift measured 40 kilograms per second hydroxyl production, equivalent to water production in late July, when the comet was 3 astronomical units from the Sun. If post-perihelion water production exceeds 100 kilograms per second, that confirms the interior has higher water content than the carbon dioxide rich surface. Closest approach to Earth during the entire visit, still no danger. 1.8 astronomical units is 269 million kilometers, 167 million miles. Farther than the Sun, no impact risk, no threat, just a visitor passing through. After Earth closest approach, 3. I-Atlas continues outbound. It passes 0.65 astronomical units from Venus on November 3rd. It passes 0.36 astronomical units from Jupiter on March 16th, 2026, 54 million kilometers from Jupiter. Close enough that Jupiter's gravity will perturb the trajectory slightly. Not enough to capture the comet, but enough to change the outbound velocity by a fraction of a percent. The comet will drift back into interstellar space at roughly 60 kilometers per second, relative to the Sun's rest frame. It will take tens of thousands of years to reach the nearest stars. It will pass through the galactic disk, crossing spiral arms, dodging dust clouds, enduring cosmic ray bombardment. Eventually, it will approach another star, maybe in 1 million years, maybe in 1 billion years. A carbon dioxide-rich comet with Earth like carbon isotopes, evidence of formation in a solar-type star's disk, a nucleus scarred by passage through a yellow dwarf star's radiation field in the year 2025. The ions scatter into interstellar space, the magnetic field lines relax, the plasma disperses. Within weeks of leaving the inner solar system, the tail vanishes. The comet becomes dormant again, surface ice reforms, the coma collapses, the nucleus goes dark. But for 5 months in 2025, 3I Atlas burned bright. It showed us what a carbon dioxide comet looks like. It showed us how interstellar objects interact with solar wind. It showed us the physics of mass loading and ion pickup at high gas production rates. It gave us a chance, however slim, to sample material from another world via Europa Clipper. All of these factors align or they do not. If they align, we get data. If they do not, we get nothing. You work with what you get. You make the measurements you can. You publish the results. You move on. It is a frozen rock following a hyperbolic trajectory determined by gravitational forces and initial conditions set billions of years ago when it was ejected from a disk around a star we will never see. It carries no memory of the sun, no record of the solar-wind interaction, no knowledge that Europa Clipper tried to taste its tail. It just flies, outbound, into the dark, forever. Europa Clipper sits 186 million miles away, waiting for ions that may or may not arrive. Instruments on or off, solar wind fast or slow, tail wide or narrow, ion density high or low. UV photons ionize gas, solar wind magnetic field picks up ions, particles accelerate antisolar, the tail grows. Just momentum transfer, magnetic coupling, and 200 Kelvin surface ice screaming into plasma at the rate of tons per second, while a spacecraft 100 million miles away hopes for a single ion to trip a detector. No course corrections. And in December, when the comet reemerges and we point every telescope we have at the nucleus, we will see if Perihelion cracked it open or left it whole. Because that is what solar wind and radiation do to ice. They do not negotiate. They heat, they ionize, they strip, they sculpt. 3. IATLAS learned this on October 29th, the hard way.